past, actually, right? Are we mentioning that?
Thank God.
So, thank God, yes, Ellie. Thank God for those things. We're going to see that we only have 3 sections, right? Or it's test 11, rather. Test 11.
Actually, I would go to.
We've got 20-2,
I put 10.
20-3, and then 9-1. 20-2 and 3 were very similar in nature. It had to do with circuits, okay, the basics of circuits. Now, we talked about a lot with circuits in the past. There's a lot of things we've done. There's a good amount of math with circuitry you can do. We did a few example problems. Let's talk about our rules first. We've got some rules for parallel and series. Let's talk about the nature of those rules and maybe explain why they make sense. So let's first start with series. It's the easy one to do. Okay, so let's draw ourselves a quick series circuit. Simple series circuit. Remember, a series circuit is anything that does not split its path along the way from one terminal to the other. It's the easiest way to recognize something in series. I could have 2 batteries here, and those batteries would be in series. Right now I have a battery and 3 resistors. Maybe I'm going to, make one of those resistors a bulb.
There's no branches. There's no branches.
There's no branches, exactly. No branches for it. Maybe I'm also going to draw on a switch right here. Okay, I'm going to leave that switch open.
This is 22, right?
Yeah, 22 and 23. They're kind of the same, In 23 we took, remember, parallel and series combinations and reduced them. So we'll do an example of that. So in this circuit, we can see that the flow is continuous in one direction from the positive terminal, out the positive terminal, and back into the negative terminal. Now, clearly because the switch is open, this flow will not actually occur. When the field is established, when the switch is closed, the field is what gets these charged carriers to move through the actual circuit. Does that make sense? Okay? Closing the switch establishes an electric field which allows the charged carriers to flow through the circuit. So that allows us to understand our rule for current. What's the rule for current? The current in the circuit when in series.
I don't actually know for sure. I was going to say for resistors, you just add resistors.
For resistors, we just add them up. Good. And we derived that earlier. So I'll write that one down. So there's resistance. For equivalent resistance of all the resistors, you just sum them together. What about for current?
They're all equal.
Why are they all equal? Klaus?
Because in a series circuit, they get the same amount of voltage.
Be careful. You're using your words because voltage they don't. Remember? The current across each resistor is the same. Why is that? Is my question. What was the analogy we thought about for current? Anyone remember? The flow in a pipe. If that pipe does not split, is the flow going to change really? No. The flow comes from the pressure above. If the pipe has a decline to it, the pressure above is going to be a consistent value. It'll pick up speed because of gravity, obviously. But the flow rate in a controlled system is like having flow rate gauges along the way. Those flow rate gauges measure the flow through the circuit. That's what the resistor at these locations can tell you. That the current at each location is the same. It's when there's a branching off that part of the current goes one way and part goes the other way. Bless you. So that's how you remember for parallel, the current is not the same in each for parallel. Okay, so this is series we're talking about. The third part is voltage. And if you remember, voltage drops along the way. That's why it's called a voltage drop. The voltage itself drops. So let's say we have a 9-volt battery and you connect it to a circuit. And you have 3 bulbs or 3 resistors as seen here. If there's 9 volts supplied by this battery and I close this switch, it means that those 9 volts are being given to each resistor. The question is how much goes to each, and that's usually, not usually, but really a function of the actual resistor itself. Okay, the actual resistor itself. How do you calculate voltage? Ohm's law. Voltage. V equals IR. So the voltage going through a resistor is based on the current through that resistor. Oh, take a look. It's the same, isn't it, for all resistors here? So the voltage going through a resistor is really only based on the resistor's resistance. Take a look at this. It makes sense. Again, the voltage across each resistor is a function of current, which is the same for each resistor, so that doesn't affect it, and times resistance. Well, the resistance across each resistor, the resistance is a material property. It's like density. It's a property of the resistor itself. Okay? So each resistor takes on a different amount of voltage, but altogether it takes on the total voltage supplied. So what would that say? How would I write that? How would I write like my, I wrote my I equation, my R equation. What's my V equation that should go here? V equals what? Good. V1 plus V2, dot, dot, dot. Those are my 3 rules there in white. The current in a series circuit is the same. The voltage provided in the circuit equals the voltage, the sum of the voltages to each resistor. The overall resistance in the circuit is the sum of each resistance itself. Yes? That's what voltage is.
So when you add,
Yeah, if the word asks for voltage drop, potential difference, change in voltage, that's what I'm talking about for voltage, yeah. Okay? Remember guys, the voltage is just saying that in the beginning the charge carriers have a lot of potential energy. And then what happens? The charge carriers go through the resistor. The resistor uses that energy and thus it decreases potential energy. When it gets back to the battery, it's got no potential energy in the charge carriers. They get recharged because the battery does work to them, and then they go back to the circuit. So the potential difference is the charge carrier's potential difference from one end to the other. That's where that word comes from, in that term. It has a lot of potential in the beginning, no potential at the end, it regains potential. That potential difference is 9 volts. Okay? That's a great question, because we didn't talk about that too much. Okay, but that term has been coming up in your text, I'm sure, in problems too.
So there's always a potential difference in like every circuit. Like there's always like a little change in the voltage.
There has to be. If there's no potential difference is the same thing as like potential energy. If I were to drop this, it moves because of the change in potential energy. Well, if I put this here and I drop it, is there any change in potential from where I just held it to the table?
No.
So nothing happens. There's no driving force. It's equivalent of like pressure in a hose. If there's no pressure being provided to push the water forth, is it going to flow out? No. Usually gravity provides a lot of that pressure for water, right? That's how like streams and rivers run, via gravity. There's a driving force, it's gravity. Here, what's the driving force? The difference in the potential at each terminal. High potential, low potential causes this to push itself through. We should be able to simplify a series circuit and come up with the current and the resistance and the voltage through each of them. We did an example of this in 20-2, where we had 4 bulbs lined up in series. Then we did the same 4 bulbs in parallel, and we analyzed the voltage drop across each bulb. We analyzed all that stuff. You should be able to do that. So if you wanted to, for a sample question, sample, if you're practicing. Let's say I give you the following. Here's your diagram. And the question would say the following. Oops, let me give you a voltage supply. Let's say 120 volts. Determine the current Determine the current in the circuit shown below. Determine the current in the circuit shown below. Then, you can write this down if you want because you can practice this tonight. Determine the current in the circuit below. Then determine the voltage drop across each resistor. Determine the current in the circuit below. Then determine the voltage drop across each resistor. Now, if you want the current in the whole entire circuit, you need to have the voltage for the whole circuit. Well, you have it. What's the voltage for the whole circuit? 120. But do you have the resistance for the whole circuit? So what do you have to do first with these kinds of problems?
Find the total resistance.
Find REQ, the equivalent resistance. Well, in series, what did our rule tell us to do in series? We add them up. 2 plus 4 plus 1 is 7. Very easy. So you go ahead and do this, please. If that's the case, well, look at that. I've got resistance. I've got voltage. Let's go ahead and use Ohm's law. Go ahead and use Ohm's law. The current is going to equal the voltage over the equivalent resistance. So 120 over 7. 120 over 6 is 20. So it's going to be a little bit less than 20 something. What do you got? 120 over 7. And these are going to be measured in amps. Remember, current is measured in amps. So you've accomplished part A of the problem. I'm telling you now, just so you know, you're going to have problems with this. You're going to have a problem where you're going to have series and parallel. Okay, one will be series, one will be parallel. You have to do them both. And then I'm going to give you something where it's series and parallel in one circuit, and you have to just simplify it. Okay, maybe not do as much math. What was the second part I asked you to do for this problem?
Find the resistor, or find the current in each resistor.
Find the
potential difference in each resistor.
Yes, the voltage drop or the potential difference in each resistor. How do you find voltage? V equals IR. Well, this I that you just determined, 17.1, is the same current for every resistor because it's in series. When in series, the current is the same. So for resistor number 1, it's 2 ohms resistance. If the resistance is 2 ohms, that goes in for R right here. If the current is 17.1, that goes in for I. And you can find the voltage across the first resistor. Again, voltage across the first resistor is the current across the first resistor times the first resistor itself. As a result, the current is the same for all of these elements. The resistance is what varies. 34.2 volts. Do I need to rewrite the equation 3 times? Definitely not. Please don't write, you don't write V2 equals I2 R2, V3 equals I3. We did that in our notes to establish that idea. But at this point, recognize that it's just current times resistance for each of these resistors. What does V2 and V3 turn out to be? V2, 4 times 17.1, 68.4. And then finally 1 times 17.1. Okay? What can we recognize? What can we recognize? What should you do with these 3 numbers to make sure that they're right? Add them. What do you get, Zoe? 120. It's not a coincidence. The voltage supplied to each resistor sums together to give you the total voltage supplied to the network. Okay? Yes? So, how do you practice this? You make up your own problem. Pick different resistances. That's it. It's not hard. Literally, change those numbers. Use 5 resistors instead. Use 3. I don't care. Whatever. But just change it up and practice. That's all you have to do. It should be really, really straightforward. In parallel, it's really straightforward also. Okay, parallel is very straightforward as well. Let's prove that now. Look at this. Ready? Battery. 1, 2, 3, 4, 5 resistors. Each with resistances of 1, 2, 3, 4, 5 respectively. And we'll say it's a 120 volt source. Okay? That's a whole lot of resistance. Now, since it's in parallel, we think about our parallel laws. And before we can begin this problem, I need to tell you what the problem would ask. This problem would ask the following. Determine the current provided by the voltage. Determine the current provided by the voltage. Then, these are like your hints, by the way, as to your rules. Then determine the current in each or across each resistor, which will clearly tell you that those are going to be different, right? We know that because it's branching off. When it branches off, the current is different for each resistor. So determine the current in the system, then determine the current across each resistor. So we need to simplify this so that we have one voltage, one resistor. In parallel, what do I do? In parallel. Very good. 1 over REQ, and this is one of your formulas. It says it on your formula sheet if you need to look. Equals 1 over 1, plus 1 over 2, plus 1 over 3, plus 1/4, plus 1/5. Yes, sir.
And are those just responding to the resistors? Those aren't the actual numbers you use?
No, those are the numbers I'm saying. Those are like, I didn't put units. These are 1 ohms, 2 ohms, 3 ohms, 4 ohms, 5 ohms. Okay? Add them up, please. I'm not going to do it. Do it on your calculator. Please don't do this by hand. Don't put it on LCD. Do it on your calculator. It's much faster. What do you get on your calculator? 2.28.
Should we put the decimal answers?
Well, we have to find the equivalent resistance. So you didn't invert this yet, right?
No, that wasn't inverted. Yeah.
So now let's invert it and see what we get.
To invert, you just multiply, or you take it to the negative first power, right?
It's the exact same thing as inverting a fraction. X to the negative 1. Good.
0.438.
Wait, to invert it, you just click X to the negative 1.
Correct. Or just do 1 over 2.28. Either way. There's also a way to convert decimals to fractions on the calculator. So when you got 2.28 with all those extra decimals, you could have hit math, enter, to convert it to a fraction, and then you could just take the reciprocal of that fraction. Same thing.
Should that be in ohms?
Thank you. It should be in ohms. Thank you. Typo. What's measured in amps, obviously? Current. So, we have the equivalent resistance now. So let's redraw the circuit with one resistor and one battery. Here's your battery, or your voltage supplied. Wouldn't really be a battery, that's a strong battery. And here's your one resistor now. This is really the equivalent circuit. Okay? So as a result, you can find the current, V equals IR. Go ahead and do it. Same way you did it last time. V equals IR tells me that I is equal to V over R. Voltage is 120. Divided by the 0.43 is going to at least double it. So we're looking at 200 and change. What do you got in?
273.6.
I got 279.
Did you use 0.43 times? 0.43?
Yeah.
I use the whole thing.
Ah.
I use it rounded down, so that works too, yeah.
Yeah. It depends on how you round. If you're doing this, you really should keep all those decimals in the calculator, and you should do 120 divided by second answer from the previous answer on your calculator. To get a more precise answer, really, that's the only reason. And the units here are amps. The units there are amps. Why is this a lot of current? The last example, what was the current, please? Go back. What was the last example's current? Natalie, what was it?
17.1.
17.1. And now we got 273. Why is that? Why is that? Yeah, look. You're taking voltage divided by resistance. This is a very low resistance that you're dividing by. Low resistance means high current. Because resistance is the opposition to current. That's why we have to know what these physically mean. So parallel circuits give low resistance, high current circuits. Series is higher resistance and lower current. Okay? Now I want you to find the current across each resistor. Find the current across each resistor.
What does the 2.28 mean?
The 2.28 was the sum of all those fractions you see at the top there.
But how do you get 0.43 from 2.2?
Well, because it's 1 over REQ, right? I need to get REQ by itself. So switch REQ and 2.8.
Oh.
And you'll get 1 over that, which gives you 0.43. So we want the current across each resistor. What is the voltage to each resistor when it's in parallel? Look at your laws in parallel. Look at your parallel laws. What do the laws tell me about voltage? It's on your formula sheet. What do the laws tell me?
Isn't it like you just had?
That's in series.
It's the opposite.
It's the opposite. So what is the opposite? They're all equal. The voltage supplied from the power source goes to each resistor when in parallel. You need to familiarize yourselves, seriously, with your formula sheet, with those 6 formulas, okay? You really need to. The current is different through each resistor. The voltage is the same. So everything is going to be 120, except now it's divided by the actual resistance. Well, the first one is 1 ohm. So the first one is going to be 120 amps. The second one was 2 ohms. I'm not going to keep writing all this out, by the way. Okay, there's the second one right there. And then I keep going. The third one is 120 over 3, which is 40. 120 over 4 was the fourth one, which is 30. And then 120 over 5. 25? 24. Yeah, because 125 would be. Okay, and if we add all these up, we should get around 274. And look at the actual current that we had. 273.6. Okay, it's not a coincidence. This is 180, 220, 250, 270, 274. 273.6. The sum of the currents across each resistor equals the current provided by the network. Now, I might ask you a follow-up question. And this really comes from your lab, and a lot of you guys butchered this on the lab, so you might want to listen in. If I ask you about the power provided to each of these bulbs, which I did in the lab, you could calculate it. What's power equal to? Power equals current times voltage. Well, you've got the current to each resistor. The voltage is 120 no matter what. So all you have to do is take your answer of 120 in amps and multiply the 120 here, or 60 times 120, or 40 times 120. But you can clearly conclude which of these resistors gets the most power. Which one? Why? Yeah, it's the highest product. To get power, it's current times voltage. The first one will be 120 times 120. The second will be 120 times 60. The third will be 120 times 40. Then 120 times 30. Then 120 times 24. So the more resistance in the bulb, the brighter it's going to be, the more power you are utilizing for that bulb. Okay, so I could ask you about power to individual bulbs because all you need is current and voltage to get power. I might give you, this is a good hint, I might give you a parallel and a series circuit with the exact same resistors. Because when you do that, you're going to get completely different answers. And I might ask you to analyze that and discuss it. Okay, so your notes, the examples from your notes are good ones that we did talk about, but we didn't go as far as power. That's where you did that in your lab. Okay, and a lot of people struggle with that, I'm telling you now. So please remember, power equals current times voltage. There are 3 power formulas, but if you have current and you have voltage, it's the easiest one to use. For circuitry that we have to consider is reducing a complex circuit. So, you can draw any circuit you want and do this for it. Okay, you can do anything you want with circuitry, you just have to know what you're reducing. So I'm going to draw an arbitrary circuit. I'm literally making this up on the spot. So you can do this yourself. Let's take a look at this circuit. And it looks complicated because of the way it's set up, but it's not. You just have series and parallel together. That's what's going on. So, the first thing that I start to notice is this. Here's what I start to notice. This current branches between here and here. Part of it's going to go to here, part of it's going to go to here. And then when it gets over here, we have to consider the fact that this has to come back through here. Actually, would this circuit be legitimate? Maybe I can't even do this. Because it looks like the flow would screw up. I can't erase it. It's not erased. Whatever. Let's say for the sake that this is actually a circuit that would work. I would see this, and this as what? Again, 1, 2, 3. Parallel. I mean, they're literally parallel, and you see that there's branching off in each section. Now, these two themselves are what? They're also parallel, but only with each other. These two are series. Again, from this resistor to this one, is there any branching between? No, there's not. But from this resistor and this one, there's a branching that occurs. So parallel, series, reduce those first. So let's pick numbers. Reduce the top one. Replace it with how much? 6. Easy. Top one's real easy. The bottom is 8. How about the middle?
8 over 7. Open in 7 over 8.
What are you getting, Fatma?
8, I got 7 over 8.
7 over 8?
Because it's 8, because it's, you can just...
You're going to do 1 over 7 plus 1 over 1.
Yeah, which is 7 over 7. And you add
8 sevenths. That's 1 over REQ, so 7 eighths. Very good. So 7 eighths means the middle one's going to be 0.875?
Wouldn't it be 1
Yeah,
plus
0.87.
1 over 7?
0.875? Say again? Right, 1 over 1 plus 1 over 7 equals 1 over R. I'm doing the middle, okay? We're looking at the middle piece right here. That's what you would do because it's in parallel. That gives you 8 sevenths. Because I can do a fraction very easily. 1 over 1 is 7 over 7, really. 8 sevenths is 1 over REQ, so REQ is 7 eighths. And 7 eighths is 0.875. Yes?
Aren't 2, 4, and 8 in series though?
They're actually not because of the fact that there's this branch right here. Like, look, follow the flow. There's a branching off before it gets to this piece, which means that there's something else. And if you look at this, you can see here that there's that branch again. Okay? So these three...
So would 6.875 and 8 all be in parallel?
That's correct. So these last 3 that you have now, after you've reduced these, are all in parallel.
Oh.
Follow the flow, right? This is going to branch here. This is going to branch here. Branch here. These 3 would be considered to be in parallel now. So you add those three fractions together. Again, 1/6, 1 over 0.875, and 1 over 8. And then go ahead and solve for REQ. Joe, you got it?
It's 0.69.
All right, 0.7.
Wait, where did you get the 8 and 7 from? Like,
If you go back up to the first circuit, look at the middle branch.
yeah,
You have 1 over 1 and 1 over 7.
yeah.
So there's the 1 over 1 plus 1 over 7 equals 8 over 7. All right, add, I mean, these are just simple math. Add these two fractions together.
Yeah.
I wasn't doing it on my calculator because of the nature of the problem. Okay, so we started with a 9-volt battery. And we have an overall resistance of 0.7. We could find the current in this circuit also. Now, I'm not going to ask you to find the current and voltage across each resistor here because those rules get a lot, well, not a lot, but a little bit more tricky. You have to work your way back every time to get the current here, across each, then go back to the previous step to get the current across each. Okay, so for this kind of a circuit, all I'm asking you to do is reduce. Reduce, reduce, reduce. Let's quickly talk about it for a while yesterday. What I do want to do is reiterate several things. If an object floats, what do you know? These are the important things we want to jot down real quick. If it floats, what are some things you know? Give me anything. Go, Katie.
It's less density.
Yeah, the density of the object has to be less than the fluid. If it sinks, what happens? Good. It could be equal in density, and we have that like in limbo stage. What else? Yeah.
The going force is equal to the force of gravity.
If it's floating, what's keeping it up? Buoyancy. Buoyancy balances gravity. If it sinks, then what do we know?
Gravity is greater than buoyancy.
Yeah, buoyancy has got to be less than gravity. Oops. Or less than gravity. There we go. What else? There's one other thing, actually. And we haven't really written this down in a table, but we utilize this in a lot of problems. It has to do with volume.
When it's sinking, the volumes are equal.
Yeah. This is true. When it sinks, please, do you understand this still? This is Archimedes' theory of displacement, or principle of displacement here. If a certain object is submerged underwater, the amount of fluid displaced equals the object itself. These are equivalent. So whenever an object is fully submerged, the volume of the object would equal VF. If it's not fully submerged, they're not going to be equal. The volume of the object will always be greater than the volume of the fluid displaced. Always. Because if I'm sitting on the surface, and part of my body is above the fluid, and part of it is below the fluid, only the part that's below the fluid displaces water. So VF, when it's floating, write this down, in words maybe. VF, under the floating category, VF is equal to the part of the object that's submerged. Let's write that down again. VF, when floating, is equal to the part of the object that has been submerged. Benno.
And does that matter when it's floating? Because there's only one point of contact on the water when something's floating, right?
Yeah, but it depends on how much it's floating. So like a bar of soap that is 3/4 of the way submerged versus halfway submerged versus a quarter of the way submerged affects the different amount of volume. Okay?
Can we do one of the problems from the homework?
Sure. What do you got?
I think, I don't know how this was. Oh, it's number 4 on the bottom of page 324.
324, number 4.
Yeah, at the bottom of the page.
A submerged submarine alters its buoyancy so that it initially accelerates upward. Oh, this is a good one. I'm not going to give you one on the test with acceleration, but I'll go over this because it's something that if you can understand this, you'll definitely get the other ones. So it accelerates upward. What is the submarine's average density at this time? So we know, ready? For an object to be accelerating upward, the buoyancy has to be greater than gravity. That's what we know about this free body diagram here. For it to be moving upward, buoyancy has to counteract gravity, has to be more. So we know that buoyancy minus gravity is not equal to 0 anymore. We've been setting it equal to 0 for everything because I've been telling you it's fully submerged or it's floating, not it's moving. But if it's moving, you just have MA. All right, now we have to go ahead and look and see what we have. So if we're trying to figure out, it looks like we're trying to find out the average density of the submarine. So buoyancy, rho F, V, F, G. Gravity, mass of the object, G, equals mass of the object times A. These are the equations that we know. We know weight is mg. We know buoyancy is always this. Vf is the same thing as the actual volume of the object. It has no effect on this. It has absolutely no effect on this. But we're going to need to solve, it looks like, to get the average density of the submarine, we're going to have to plug in with the volume. So let's go ahead and do this. What is mass equivalent to? What can I replace this MO with? PV. Rho times V is equal to mass. Where does that come from? That comes from rho equals mass over volume. So I could use this in for mass. So rho O V O. That mass of the object on the right-hand side could also be replaced with rho V. This is the mass of the object still. Mass equals density times volume. What can I do since it's in everything? If an object is fully submerged, the volume of the fluid equals the volume of the object. Bless you. Yes. Cancel all 3 V's to start. Okay? Now after that, all you're left with, rho F is the density of salt water. Gravity is 9.81. Rho O is unknown. Gravity is 9.81. Rho O is unknown, and we were told that this was accelerating at 0.325 upward. So all you have to do for this now is solve for rho O. It's in 2 spots. So just combine like terms, add 9.81 rho to this side, add the 9.81 to 0.325, and then divide by that answer. Guys, this is a really good problem to look at. Okay, you should definitely look at this kind of a problem. Again, I'm not going to have something that's accelerating, but this, if you can do this, you can do the other problems. So this is a great example to utilize.
Mr. Howell, can I meet with you after science club tomorrow?